Welcome to the electronicshobbyblog.com. Today we're going to cover a specific component, the 555 timer. 555 timers have been around for a long time. They're one of the first components that I learned about when I started in electronics. In fact, the original Commodore 128 used a 555 timer to hold the reset line low for 4 seconds during startup. I think it's particularly appropriate to cover the 555 timer now, since we just finished talking about resistors and capacitors. And it's a resistor and capacitor pair that sets the pulse width, or frequency, for a 555 timer. The timer operates in two modes. Monostable mode, where it emits a single pulse for a specified time based on a trigger input, and astable mode, where it emits a continuous stream of pulses at a given frequency and duty cycle that's determined by a capacitor and two resistors. We'll look at both of those in theory and in the lab. In fact, I've already got our first circuit set up on the bench. So let's get to it. Here you see the equivalent circuit of the 555 timer on the right. And then on the left, you can see the actual circuit consists of a number of transistors and resistors. All in all, it's not a very complex device. It has 8 pins labeled 1 through 8. Each pin has a specific function. Pin 1 is always ground, and pin 8 is always the supply voltage. Pins 2, 6, and 7 are used to control the timing for either the monostable or astable modes. Pin 4 can be used to reset the device, and pin 5 controls the threshold and trigger levels. Here's an excerpt from the datasheet that shows a number of the basic parameters for the 555. The 555 is a CMOS device, and as such, it has a very wide voltage operating range, from a minimum of 4.5 volts up to a maximum of 16 volts. Here's an example circuit for monostable operation. In monostable operation, a trigger pulse causes a single output pulse equal in duration to the value set by RA and C in this case. So the length of that pulse is equal to 1.1 times RA in ohms times C in farads. When the voltage reaches 2/3 of VCC, the flip-flop resets and the capacitor discharges. So that sets the output state low. Now what's really interesting about that is you'll recall when we were talking about tau, right? Tau is the value in time that it takes for the capacitor to charge to 2/3 of VCC. So here, this kind of directly supports what we talked about in our last lesson on capacitors. Here's another example of a 555 timer set up for monostable operation. Let's go through and look at what happens. Let's say it starts discharged, meaning that the output is low. And then there's a trigger pulse that falls below at least 1/3 of VCC. When that happens, the output automatically goes high, and C1 starts to charge through R1. Once it charges to 2/3 VCC, then the output goes low, and C1 discharges, and it's ready for the next trigger. The width of the pulse is equal to 1.1 times R1 in ohms times C1 in farads. And you can make that pulse as narrow or as wide as you want. Another important thing to note is that a 555 set up for monostable operation in this configuration will continue to trigger if it continues to receive trigger pulses. That is, if the output is high and a second trigger occurs while the output is high, then it will continue to stay high. And it will stay high until T time after the last trigger. Let's set this circuit up in the lab and see how it works. So we're going to try two different configurations. In the first configuration, well actually in both configurations, we're going to use a 10K resistor for R1. And then we're going to use both a 47 microfarad and we'll try it also with a 470 microfarad capacitor. And you can see how the pulse width will vary. And we'll look at a couple of different examples. So I've got this set so that whenever I push the switch, it gets a trigger pulse. So first with the 47 microfarad capacitor, and you can see that the light stays on for about half a second. And then we'll switch to the 470 microfarad capacitor. And you'll see that the light will stay on for about 5 seconds. Now here's something really neat. If you leave the trigger floating and you give it a long enough time period, you can make it act as a touch switch. So in this example, the only thing I've done is to take the switch out and simply use a wire attached to the trigger as the touch sensor. Now let's look at astable operation. This is where the 555 will put out a continuous stream of pulses. And the pulse width, both the high portion of the pulse and the low portion of the pulse, will be controlled by resistors and capacitors. So in this configuration, we actually have two resistors, RA and RB, and a single capacitor, C, that control the frequency and the duty cycle, the time it's high versus the time it's low. And those switch on and off based on the capacitor charging and discharging between 1/3 and 2/3 VCC. So again, you'll recall tau, and with tau when we're charging, the first tau we charge to 2/3 of VCC, and in the second tau we discharge by 2/3 of VCC, which would be 1/3. So here's another view of a circuit for astable operation. And let's take a look at this and go through step by step what happens. So we'll start with the capacitor discharged, meaning the output is high. And then C1 begins to charge through both R1 and R2. Once it charges to 2/3 of VCC, the output goes low and it begins to discharge through R2. It discharges through R2 until it reaches 1/3 VCC, and then the output goes high, and the process repeats. And so you can see we've got our pulse train on the right, and high is T1 and low is T2, and we calculate T1 as being 0.694 times the sum of the two resistors times the capacitor. And for T2, which is the time that the pulse is low, it's equal to 0.694 times just R2 times C. And so the total period, both the pulse high and low, is T1 plus T2. And the frequency, of course, would be 1 on T. And the duty cycle is calculated as the time it's high over the total pulse width time. So here's the circuit we're going to set up in the lab. And we're going to set up two different circuits with two different resistor values. So this is the first example where we're going to use R1 equals 1K and R2 equals 10K. And then we're going to set a 47 microfarad capacitor. And what we can predict is that the pulse high time is going to be 0.359 seconds, and the pulse low time is going to be 0.326 seconds. So overall, it'll be just under 3/4 of a second. And we'll end up with a frequency of about 1.5 hertz.
Well, I hope you enjoyed that. If you did, please give it a like and subscribe so you won't miss any new content. And as always, thoughtful, on-topic comments are always appreciated. Until next time, cheers!
and the duty cycle is about 52.4%. Now it's very interesting to note that with a 555 timer, you cannot achieve a 50% duty cycle. You can get really close. Because you have to have R1 with a value other than 0, you can't achieve a perfect 50% duty cycle. Here's that circuit in the lab. You can see that 1.5 hertz flash rate, and you can also see that the LED is on for pretty close to the same amount of time it's off. At least I can't tell the difference by looking at it. Now let's change the resistor values. So now we're going to switch to a 10K resistor and a 2.2K resistor. In this case, we've made R1 larger than R2, so we're going to end up with a pretty different high time versus low time, or a very high duty cycle. We're still using the same 47 microfarad capacitor. So if we look at the pulse train now and do our calculations, we'll get that T1 is going to be equal to about 0.4 seconds, pretty close, 0.397. And then T2 is going to be equal to about 0.07 seconds. Now keep in mind, we're calculating these out to 3 decimal places, but that's probably not very realistic because the capacitor itself has about a 20% tolerance rating, and then the resistors have about a 5% tolerance rating. So when you consider the tolerances and the fact that we're going out to 3 decimal places, yeah, probably good to 1, if any. The total period is going to be about 0.5 seconds. So we should end up with a little over a 2 hertz flash rate. And you can see that the duty cycle is 84.6%. That means that the light should be on quite a bit longer than it's off. Let's take a look and see. And here you can see that the light flashes pretty close to what we predicted.
Well, I hope you enjoyed that. If you did, please give it a like and subscribe so you won't miss any new content. And as always, thoughtful, on-topic comments are always appreciated. Until next time, cheers!